Welcome to Maths with EJD. In this video, I'll be looking at linear programming still, where we consider special cases in graphical solutions. Of course, we've started already using graphical solutions to solve for linear programming problems. So, first off, I'd like to talk about these special cases that may arise when we use graphical solutions to solve linear programming problems. So there are basically three. The first one is multiple, you can have multiple optimal solutions, multiple optimal solutions. And that is what this video is about. Then another case is for infeasible solutions. So the solution may not be feasible, and then you can have unbounded solutions. Unbounded solutions. So these are special cases when we talk about the graphical graphical solutions to linear programming problems. Of course, this also brings me to quickly talk about types types of solutions we can get, types of types of solutions in linear programming problems. So types of solutions um, can be, you can have feasible solutions, right? So you can have feasible solutions. So outside of feasible solutions, you can have feasible solutions are all possible solutions you can ever get. Then you can have optimal solutions. That's actually the best solution in each case. So, but in this particular video, we are seeing the possibility of multiple optimal solutions, which we are going to get to in a moment. Then we can actually have, in addition to these two now, you can have feasible solutions, optimal solutions. Apart from that, then you can have, of course, the optimal solution can either be unique or multiple. You can have unique or multiple optimal solutions, and then you can have infeasible solutions, infeasible, just like I said before, infeasible solutions. And in addition to infeasible solutions, you can then have unbounded solutions, solutions without boundary. Okay, unbounded solutions. All right. So, but the concern of this video, the focus of this video is on a special case in graphical solution, which is about multiple optimal solutions. In our previous videos, we have already seen the possibility of feasible solutions and even the possibility of unique optimal solutions. So now the attention shifts to multiple optimal solutions. Multiple optimal solutions. Okay, that's what our focus is on in this video specifically. And this is how this proceeds. In linear programming, right? In linear programming, that's LP for short. In linear programming, a problem, a problem may have multiple optimal solutions. Multiple optimal solutions. When the objective function, when the objective function is parallel, the objective function is parallel to a constant. The objective function is parallel to a constant at the optimal value. At the optimal value. So this occurs when the optimal solution is not unique. So the optimal solution is not unique, and there are various combinations of decision variables various combinations of decision variable values that yield the same optimal value. Same optimal value for the objective function. Okay. So we have that. All right. Now, I'll give one example to demonstrate this reality, and that is this. We have this problem. Maximize x equals 8x plus 6y subject to 8x plus 6y less than or equal to 48. And then we have constraint like x is less than or equal to 9, y is less than or equal to 12. And then we have the non-negativity constraints like x is, okay, let me do it individually. X is greater than or equal to 0 and y is greater than or equal to 0. These are non-negativity constraints. So this kind of problem, now let's show how we can actually get multiple solutions from it. Of course, you can already see that 8x plus 6y will be parallel to 8x plus 6y. And we made mention of something like that previously. This occurs when the optimal solution is not unique. And okay, yeah, up there. So in it, optimal solution when the objective function is parallel, right, to a constant at the optimal value. So let's look at how this goes. So of course, we are talking about the graphical method for solving these, right? So I know what we do. We take we go with the lines. So we know this is going to give us line 1, this is line 2, and this is line 3. Okay. So, we are dealing with linear programming. So it's all about lines. So the first line, for instance, we have 8x plus 6y is less than or equal to 48. 8x plus 6y is less than or equal to, sorry, since you're dealing with line now, right? It will not be inequality anymore. So we have line 1 such that it is 8x plus 6y, 8x plus 6y is less than or equal to 48. So, and then we can try to get the corner values here, so to speak. So at x equals 0, we know that that will be 8 times 0 plus 6y is equal. Oh, I keep making this mistake. We are talking about the line now, not the inequality. So it is equal to, right? So this is equal to 48. So 8 times 0 is gone. So 6y is equal to 48. So y itself is 48 divided by 6. So y now is equal to 8. 8 times 6, I believe, is 48. Yes. Yeah. So in that case now, all of this is giving us 0, 8. Okay. Then for the same thing, right? For the same line 1, we know that at y equals 0, we have 8x plus 6 times 0 equals 48. So this is 0, right? So 8x is equal to 48. That means that x itself is 48 divided by 8, which is 6, right? And all of this is going to give, it means that when x is 6, y is 0, okay? So we have these 2 points from these 2 lines. Okay, and first, we are going to use that to draw the lines as we move on. Then another thing we can do is, we have so that's line 1 already, right? So for line 2, we have line 2. Line 2 now would be x is less than or equal to 9. That means x is equal to 9. So there's nothing we can do about that. X is equal to 9. That's just what we have. Then line 3 tells us that y is equal to 12. Line 3, y is equal to 12. So what we can now do is we can take these lines in pairs and solve them to see if there are intersections, if there are points where you don't already have. So let's see that. So if you take line 1 and line 2, for instance, so line 1 and line 2, that means 8x plus 6y is 48. 8x plus 6y is equal to 48. Line 2 tells us that x is equal to 9. So if we do that, that means that So if we put all of these together, that means we have 8 into 9 plus 6y equals 48. So 8 times 9 is 72 plus 6y equals 48. So 6y is equal to 48 minus 72. And 6y, 48 minus 72 should be minus 24. Minus 24. So y is equal to minus 4. Of course, we don't need this because, because of this non-negativity condition that y has to be greater than or equal to 0. So it means that this, okay, I should have actually changed the marker. It means that this is not acceptable. This is infeasible. Okay, in this case, this is not feasible. So we can't use this value. Okay, can we also do line 1 and line 3? Okay, line 1 and line 3. So if you take line 1 and line 3, what do we get? Line 1 again is 8x plus 6y equals 48. Okay, 8x plus 6y equals 48. And line 3 is y equals 12. Y equals 12. So if you take the two together again, we have 8x plus 6 into 12 equals 48. So that is 8x. 6 times 12 again is 72. Yeah, and that is 48. So 8x is equal to 48 minus 72. Again, we have 8x equals minus 24, and x is minus 24 divided by 8. So x is equal to minus 3. Again, x is guaranteed to be non-negative. Okay, x should be greater than or equal to 0. So in that case, also that value is not feasible. So this is infeasible again. So we can't admit this value of x. Okay, so we have done L1, L2, L1, L3. Can we do L2, L3? So if we do L1, okay, L2, L3, there's nothing we can do because they are just straight lines. We cannot solve anything there. Okay, so there's nothing we can do with them. Yeah. Or the best we can do, if we say L2, L3, right? If we say L2, L3, so that means we have x equals 9, y equals 12. Okay, x equals 9, y equals 12. If you combine the two, right, you just have 9, comma 12. Okay, so I mean, does this actually make any sense in the long run? Let's see. So until we plot now. So it means we now, how many points do we have to plot? We have 0, 8, 6, 0, 0, 8, 6, 0, and then so do we have a meeting point for this? Let's see. So let's draw our graph. So what are the points to plot again? 0, 8, 6, 0, and 9, 12. 0, 8, 6, 0, and 9, 12. So 0, 8, 6, 0, and 9, 12. So let's say this is 3, 6, 9, 12, and 15. So that's for the x-axis. For the y-axis, we do the same. 3, 6, or maybe 2 is better, right? Okay, let's just do 3. 3, 6, 9, 12, and 15. And that is y-axis. So let's see that. Okay. We have 8, 0, 8, and 6, 0. 0, 8, and 6, 0. Okay, so let's try to plot. So 0, 8, right? 0, 8. That means when x is 0, y is 8. So let's say 8 is somewhere around there. 6. So 6, 7. So this is 7, 8, and 9. Or let me space it out. 7, 8, and 9. Okay, so we have 0, 8. When x is 0, y is 8. So we have, let me do this, 0, 8. And then from the same line, we have 6, 0. 6, 0. So that is this now. So, okay, we have that straight line. The line is not so straight, so but I mean we can work with it. And the inequality is less than or equal to. So less than or equal to will be below the line, not above. So less than or equal to, that means that line and everything below it. Okay. So we have this. So this is line 1 now. So for line 2, we have x equals 9. Or better still, we can go to the inequality. X is less than or equal to 9. So x is less than or equal to 9. So for line 2 now, this is what we have. Line 2, x equals 9. So we have x equals 9. So, but then it is x is less than or equal to 9. X is less than or equal to 9. This less than or equal to. So less than or equal to 9 means everything to the left, because everything to the right is greater than. So we don't need the greater than, we need less than. So we come to the left. X is less than or equal to 9. So that's what we keep having. X is less than or equal to 9, like that. Okay. Then we also have line 3. Okay, so now this is line 2. Then for line 3, line 3, line 3 is actually y is less than or equal to 12. Y is less than or equal to 12. So I want to get another marker, another color, not black now. So let's say something really different. Let's say, uh, let's say light blue, okay? Something like this. So y is less than or equal to 12. So you see this is 12 now. This is 12, and we need y is less than or equal to 12. So it means we have to shade that line and everything under it. Y is less than or equal to 12, okay? Y is less than or equal to 12. So now the issue is the region that we are interested in is the region that contains all the 3 colors. So I see that's where you have orange. I see orange here. I see blue here, and I see green. So it means the region that has all those 3, of course, not on the negative side now. So you can always use this. You can use this as your delineation. Okay. Nothing below, nothing to the left of the x-axis, and nothing to the no negatives. That's just all I mean, right? So you have the 3 lines intersecting all that way, but then we just need this region that is bounded by the positive, by the origin, in short. So this is the region we are interested in this case. So, and once we identify this region, you also know that there are three corner points in that region, right? We have this this point. This point, you can call it A, which is 0, comma 8. X is 0, y is 8 there. Then, of course, we don't, the origin, of course, you already know that won't give you anything. Then you have this other one, which is B, and B is 6, comma 0. So those are the 2 corner points we have. Now, you know, the third point, 9, comma 12, doesn't make sense, because that will be 9, comma 12 is somewhere here. Okay, this is 9, comma 12, but it doesn't make any sense. It doesn't fall within the region, so we don't have to worry about 9, comma 12. So it's not, it doesn't help our matter here. So these are the 2 points within that region. So in this case now, we have to now invoke our, you know, the objective function. Sorry, this should have been Z, right? This is Z. Our objective function Z, which is 8x plus 6y. Okay, so we now say from, okay, of course, already the 2 points, the 2 corner points, which fall within the region. So we have we have A which is 0, comma 8, 0, comma 8, and we have B which is 6, comma 0. So we can now invoke the objective function. The objective function is it is 8x plus 6y. 8x plus 6y. So this is 8x plus 6y. Okay, so if we want to get z of a, that's objective function evaluated, that's z evaluated at 0, comma 8. That means we have 8 times 0 plus 6 times 8. So that means the objective function evaluated at that point will be 0 plus 48. So za is equal to 48. So that's the objective function. the value of the objective function at that point. Then that's not the only one. We also have b, right? So we can do zb. That means the objective function evaluated at 6, 0, okay? 6, 0. And what is the objective function? Is 8x plus 6y. So that is 8 times 6 plus 6 times 0. So this is also 0. So you see that zb is equal to 48 plus, I mean, that's just 48 in short. You can just leave it there because 6 times 0 is gone already. So you see that, of course, we already know that the optimal solution, we know that optimal solution, usually, the optimal solution usually is the maximum between ZA and ZB and any other Z there are. So that's maximum of 48 and 48. So you can see the two solutions are exactly the same. So that's 48. So here now, so we say therefore we have, or better still, let me go black again. Okay, so you can see the two different points are giving us the same optimal solution, right? So either way, you get the same value. So we can say, therefore, since since points points A, point A is 0, 8, point B is 6, 0. Since points A 0, 8 and B 6, 0 give the same optimal optimal objective function, the same objective function value, which is z equals 48. Then we have multiple optimal solutions, 0, 8 and 6, 0. So they are different, but they are giving us the same optimal solution. So that is a special case when we talk about graphical method for solving linear programming problems. So that's just the idea, basically. Okay. Now you see that this line 8x plus 6y. If you look at this line 8x plus 6y, where did I draw the line? Line 8x plus 6y. Yeah. So this is line 8x plus 6y, this L1 now. So if you try to plot the optimal solution to, it will be parallel to this. It will be actually parallel to this line, okay? So, and that is what this is about. Thank you so much for listening. If you have not subscribed to this channel, be sure to do that right away and hit the notification bell so you can always get alerted when a new video is released. Don't forget to also comment. Tell me if you need me to teach a topic or to solve a problem. Let me know. Then also like and share so that more people can have access to all this great learning. Watch out for other videos on special cases of graphical method for linear programming problems. So keep optimizing till I come your way again. Bye.